thank you all for coming here today, and thank you, Mrs. Claus, for arranging the logistics. I'd like to introduce Joe LaMagna, who's been working with me for the past 3 years. I first met Joe when he took my Introduction to Electrical Engineering course. We finished up with a 4-week set of modules where they build a device that can modulate the voice over a laser beam. Most of my students take 4 weeks, some of them take 5 weeks. Joe took 2 days, and so I knew that he was clearly a guy who needed some extra challenge. He worked with me that summer doing a Surrey project, and in that Surrey project, he completed what was, I gave him a project that was the largest and most complex project I've ever attempted at VMI. He completed the first third that first summer, so we thought we were on a good pathway to finishing it. The next third took 1.5 years to finish, and that final third, he's finishing up in the next 24 hours before he drives up to Massachusetts with the rest of his team to present it to our co-workers, our colleagues, up at the University of Western New England. It's a research device, and I'll let Joe describe it in detail. Thank you.
Thank you very much, sir. Thank you all for coming. I hope you had a good day so far. And I'm just going to jump right into it. So, the whole purpose of this project was to build a device which can measure the electrical impedance across a cell culture in a petri dish. So, the whole reason that we are doing this essentially is this is going to be used as a tool to assist in pharmaceutical drug research, and it's designed to work in an automated system. So being able to work without any kind of human intervention other than sending it up and analyzing the results. So the whole reason that we are undertaking this project has to do with the way drugs, and especially chemotherapeutic drugs, are developed. So drug development generally consists of taking your target cells, diseased cells, cancer cells, what have you, and testing them against a large database of possible drugs, possible cures. This process, it can be mostly automated. You have robotic systems that can place the cells in a petri dish, that can take the drug that you're choosing to test and put it in with the cells. The kind of bottleneck problem occurs with the fact that to observe the actual results of the drug's effect on the cell culture, you need to have a person physically take the cell out of the system and observe it. So as of right now, there's no automated way to observe how the drug is affecting the cell. And chemotherapeutic drugs especially are difficult to test their effectiveness in an automated environment because of the fact that you have to see if the drug is killing the cancerous cells but leaving the living cells without having any adverse effects on those. This bottleneck causes most commercial drugs to take about 9 years and $80 million to bring to market. So that's starting from conception, development of the drug, testing, and actually being able to put on the market so a doctor could prescribe that in a clinical setting or otherwise. So to fix this, we need a new testing strategy needs to be developed. And another place where this has effects is with doctors actually prescribing drugs, especially chemotherapeutic drugs. They don't have any way to take a specific patient's particular disease or strain of cancer and really test that to find the most effective drug. They're forced to basically choose from a short list of drugs that they've used before, that they have some familiarity with, and try to guess and pick one that they think is going to work best for the patient. So there's no way to definitively tell yet which drug is best to prescribe to a patient. So here's a proposed solution. This is a new methodology that's being researched in the past couple of years. And basically the way it works is you aim to measure the electrical impedance across the cell culture. And I'm going to get into how this works. So here you have your cell culture is suspended in this petri dish. And basically, here's your cell culture. And what it's suspended in is a conductive growth medium. So the cell culture is floating in this sort of plasma that's very conductive to electricity. That means electricity can easily flow from one end, from one electrode to the other, as you can see. So when the cell culture is small, such as in this example, there's a lot of this conductive growth medium, so current is easily able to flow from one side to the other without any resistance. However, when the cell culture grows covers up the Petri dish, also called growing to confluence. The current across the Petri dish is resistant because the cell culture is resistant to the flow of current, whereas the growth medium it was suspended in is very conductive. So, this electrical impedance, this resistance, can be measured. And the way that works is basically we apply this small current through the cell culture in the Petri dish, and what we can measure is the voltage across the Petri dish. So, kind of a way to understand how this is working is, if imagine the electrical current, it's water in a pipe. So you have a pipe, that's your wire, and the water flowing through it is the current. So how fast it's flowing, you can equate that to how high the current is. So what we're measuring over this is the voltage. Another way to think of that is the pressure on the system. So the pressure is going to change if you take your pipe and you shorten the diameter. If you make the pipe smaller, you can imagine that as increasing the electrical resistance of the pipe, and you will experience bigger pressure. So when you have greater resistance, you're going to have a greater voltage. And we can measure that, and as you can see in this graph here, this is, on the y-axis you have your voltage across the Petri dish, and here you have time on your x-axis. So you can see, in this general example, cell culture starts small and gradually grows bigger, and you can measure that as an increase in voltage, because as it grows bigger, the resistance increases, and when the resistance increases, according to Ohm's law, the voltage is going to increase as well. So if we're measuring an increase in voltage, we know that the cell culture is growing larger, and we can eventually see if it grows to fill the Petri dish or not. So using this method of testing, the process can be fully automated. We can take out that human interaction part, and we can speed up the process of testing drugs by a factor of over 1,000. And this also decreases the likelihood of contaminating the cell culture, because when you have to take it out to observe it under a microscope or other means of observation, we run the risk of introducing contaminants, possibly damaging the cells. So it's best if you don't have to take that cell culture out of the system at all. And with this method of testing, you don't have to. It can stay in that automated system from start to finish. An extra added little bonus is something like this can actually be used in a clinical setting. So doctors can use this when they're seeing their patient for, say, a scheduled appointment or whatnot. You could possibly use this system to very quickly, there on the spot, get some test results for what's the best drug to prescribe them. And I'll get a little bit more into that as the presentation goes along. So for this project, we were collaborating with a professor at Western New England University, Dr. Anthony English. He works in the biomedical department there, and he's doing a lot of this research on this new methodology. So what this method requires is a special tool. It's a custom phase-locked differential amplifier, and what this is basically is the device that we're using to measure that voltage on the Petri dish. So what we built here, and of course it wouldn't be an engineering project if we weren't building something, what we're building here is a device custom tailored to his particular research needs that's able to do exactly what he needs it to do to be able to further his research. Because at the moment, the tools that are commercially available to him are not sufficient for his testing purposes. So now I'm going to get into what the device actually is and how it operates. Right here you have a big picture diagram. So this is essentially everything that the device is condensed into block diagram form. I'll just go through it briefly. Basically you have your personal computer, your laptop, desktop, whatever, your PC, and it's the way it's talking to the device is via USB cord with a microcontroller. So a microcontroller is talking to the PC talks to the microcontroller. The microcontroller is what's controlling most of the circuitry in the device. So the way this is all set up, the microcontroller here, when it gets the command from the PC to start an experiment, it's going to talk to this digital sine wave synthesizer. What this basically does is it produces an AC voltage waveform of whatever frequency you desire. So the microcontroller will tell it to produce a voltage waveform of what frequency that you're testing at. This guy's going to say, okay, I'll make that. He makes this voltage waveform. And now this needs to go through some conditioning before it can be sent through the Petri dish. So first thing it has to go through is a high-pass filter. It's a very simple resistor-capacitor pair. And what that does is it actually centers it on 0 volts. And then it has to go through a gain stage to take it from, I think it's a little less than 1 volt peak to peak. And basically, the gain stage is going to make sure that the waveform is plus or minus 1 volt. So all this stuff, all the pieces up here, what they're doing is they're taking this voltage waveform that the synthesizer is making, and it is basically conditioning it so that it is going to be a certain waveform. And it's always going to be that certain waveform, so that we're testing with the same waveform every time, and it's centered in the range that we want to be testing it at. Now, this part right here, this is a voltage to current converter. It's a simple 1 mega ohm resistor. And the reason why we need that in there is we're sending a current through a living organism in a petri dish. So we do not want to damage the cell culture at all with a high current, because that's going to completely throw out any possibility of doing accurate tests. So what this guy is making sure that we're doing is it's taking the voltage, or rather it's taking the current, and it's going to make sure the current is 1 microamp. So it's been determined that 1 microamp is a safe current for sending through the cell cultures without harming them in any way, and without skewing test data. So that's the whole reason that we have that. So you can kind of think of this whole top portion, it's all conditioning circuitry to make the waveform that we're sending the right size and shape, basically, for running these experiments. So down here, this is the device under test. This is the Petri dish. So you have imagine the Petri dish is there. That's where your cell culture is suspended. That's where all the experimentation is taking place. What we have here is a relay. Now, the relay is used to switch the flow of current from the device under test to a calibration resistor. So the relay can be toggled back and forth, basically with just an electronically controlled switch. And what we have the testing capacitor in here, this calibration capacitor, or a calibration resistor as it was, is to give basically a set of data. So when you start the experiment, it goes through a calibration routine first. So any kind of data that it's going to get from the actual experiment, it's going to run all that through the calibration resistor first. And what that allows it to do is it allows it to basically find any errors in the waveform, any offsets, and correct them all, so that when you're getting the actual data, everything is calibrated so that you're running the same thing every time, and there's no deviation that could throw off your experiment results. All right, so moving on to the last part. So we're measuring the voltage between this point and ground. And what we need here is what's called an instrumentation amplifier. So because we're using currents of such small magnitude, the resulting voltages that we're measuring are on the same order of magnitude as background noise, essentially, in the area. So what we need to do is we need to boost the magnitude of the waveform that we're reading to such a level that we can distinguish it from background noise and other junk that's in the system. So what happens essentially is there are 4 different levels of amplification. You can keep it at ×1, so we leave the waveform the way it is, we don't do anything to it. Multiply by 10, multiply by 100, or multiply by 1,000. So the way it knows which one to multiply it by with is the computer is actually going to get the data from the lowest amplification first. It's going to see if that data is usable, if it can actually distinguish a waveform from it. If it can't, it bumps up the amplification, runs it again. So we do that routine until we find an amplification that works for the particular waveform we're testing, or we've hit the limit of the amplifier's power. So if we reach 1,000, there's nothing higher we can go from that. So that's going to be the last one that it sticks with. From that, it goes through an anti-aliasing filter, clean up the signal before it gets to the analog to digital converter, which is what's reading the waveform and translating it into a digital signal, which goes to the microcontroller and which goes to the PC. So the way that you communicate from the PC to the microcontroller is with this GUI. So this is a program that we wrote in C#. It's a simple GUI which gives you the ability to set up your experiment parameters. It shows a graph of the data that you're gathering and basic controls at the bottom. So at the top, you choose a range of frequencies to go through. So for this first generation of the device, you have an option for 10, 20, 100 hertz, and that repeats itself in increasing orders of magnitude. So 10, 20, 50, 100, 200, 500, etc., up until 100,000, which is the limit of the frequency that Dr. English required for testing. So essentially you're choosing your low frequency, your high frequency, and that's the range that it's going to test in at those frequency points that I mentioned. In this middle section, you choose basically how long you'll be taking readings. What this essentially does is this controls how many data points per frequency. So what you're doing is, say it's at 0.1 right now, so with a current sampling frequency of 1 kilosamples per second, it's going to take 100 samples because you're taking all your samples over a period of 0.1 seconds. So this is just controlling how many samples you take per frequency. And you'll take this same number of samples for each frequency on that range that you selected. This control right here selects how long you wait between completing a Bode plot to take another reading. So what you're building essentially is you're building a series of Bode plots, and this shows the magnitude and the phase of the voltage waveform that you're reading across a range of frequencies. So the range of frequencies you select in here, all that is for one Bode plot. So it does all those readings for one Bode plot, and then if you wanted to do more Bode plots, you specify that there, and it'll move on to the next one. So this control is selecting how long you wait before you move on to the next Bode plot. So depending on what kind of experiment you want to run, you might want to wait 30 minutes, an hour, a couple hours in between taking your readings because you're waiting for the cell culture to grow or show some sort of activity. So all these essentially allow you to control how you're running your experiment. The graph right here shows the current Bode plot that you're creating. So every time it finishes compiling the data and making a Bode plot, it's going to display that in this graph here. And so each time you create a new one, it'll update the graph, change the next one. It's just a way of basically seeing if your results, how the experiment is progressing, if your results look the way that you want them to, etc. Down here we have just basic start button, abort button if you're in the middle of experiment and you decide that you need to fix something, you want to end the experiment, you can end it early by using the abort button, and it has a button to save the location. So a little extra feature that we built into this is we didn't want the possibility of you running, say, a multi-day experiment and someone trips over the power cord in your lab, your computer shuts off, and you lose all your data. So as it goes along, each time it finishes one Bode plot, it'll actually save all that data onto the computer before moving on to the next one. So if it gets cut off in the middle, power goes out, whatever, you're not going to lose your entire experiment. You'll only lose what you haven't completed. So everything you've completed so far gets saved as it's completed. So there is no risk of losing that data. So this explains a little bit more how the conditioning circuitry works. They said you have the DDS that's making the waveform. High-pass filter is going to center this waveform on 0, and the gain stage is just going to boost it so that it's plus and minus 1 volt. There's a closer look at how this is operating. As you can see, I've replaced this with the Petri dish to kind of show you that this is our device under test. This is what we're using to run the experiments. You have your calibration resistor and the instrumentation amplifier. So this is getting into sort of the lower level schematic. And I won't go into too much detail, but you can see on this side we have, this is the microcontroller. We're using a microcontroller called a Thesis 3.1. It's small, it's powerful, and it's able to accomplish everything that we need it to do. Control signals from the microcontroller control the DDS, the sine wave synthesizer, and you have your basic gain stage, high pass filter, and this is a potentiometer circuit that we have in here. So potentiometer is a knob that you can tune to adjust the resistance, and the reason we have that in there is because we need to actually manually fine tune it to get it as close to centered on 0 volts as possible, and the calibration routine takes care of the rest of the inaccuracy in that. So the idea is get it as close to 0 as possible. The calibration routine will fix whatever we weren't able to accomplish there. Then it goes to its basic 1 mega ohm resistor and goes to the device under test down there. This is the 8th order Butterworth filter, a large monster of a circuit which filters the signal and conditions it so that it's good to be read in by the ADC. So I'm just going to talk about the ADC real quick. What we use is an LTC 2328 chip. It's made by Linear Technologies, and what it is essentially is an 18-bit precision analog to digital converter. So what it's doing is it takes the voltage signal, which is an analog signal, and it's going to read it in, convert it to a digital signal, which can be sent to the computer and analyzed. Now, as per Dr. English's requirements, this had to have a high level of precision. So we went with this 18-bit converter, which gives us a resolution of 3.81 times 10 to the negative 6 volts. So that's the increments at which it can read data. So every value it's reading in is going to be in some increment of this really small number. So as you can deduce, it's given extraordinarily precise measurements, which is exactly what Dr. English needs for his experimentation. All right, now this is a schematic that we built using a program called DipTrace. So what this is essentially the printed circuit board for our device, because what we want to give to him when we complete it is a fully enclosed device, essentially. So right now, everything is made on a solderless breadboard, which is used just for prototyping. So for the final version, we want everything to be soldered into this nice printed circuit board. And here's an actual picture of what the circuit board looks like. And actually, at the end of my presentation, I have it up here if you want to come up and take a look. It's actually kind of cool. So the last section of the device is this chip called an FPGA. Now, the whole reason we needed this is because the microcontroller, as good as it is, does not have enough memory and cannot operate fast enough to meet Dr. English's needs. The maximum sort of speed at which he wants to run his experiments are 100,000 hertz or 100 kilohertz. This means that we need to have a sampling frequency of 4 times that to make sure that we're getting good data. So that means if we're running at the max, we can have upwards of 12 million bytes of data, because each sample requires 3 bytes to store the information. So at full capacity, we're running 400 kilosamples per second, 3 bytes per. We're up at 12 million bytes per loading plot. Otherwise, 12 megabytes. So the TC doesn't have anywhere nearly as close to the memory to store that much data, and it also can't operate at 400 kilosamples per second. The fastest that we've been able to make the sampling frequency using just the microcontroller was 1 kilosample per second before we started to get errors in the data collection. So what the FPGA does is it's a buffer essentially between the TC, our microcontroller, and between the analog to digital converter. So the analog to digital converter can operate at ridiculously high speeds. That's not the issue. It's fine with everything that the experiment needs to run. So what happens is the microcontroller receives a signal from the PC saying, hey, I need you to start this experiment. And this is a little thing which shows you. It says, hey, FPGA, I'd like some data, please. We're starting the experiment. FPGA says, okay. And analog to digital converter, we're starting this experiment. I need you to take this many readings. And it'll give it a number of how many readings it wants to take. And he says, okay, I just took all those readings.